One final thing we want to touch base on for characterizing acids is what's called pKa. So when we've looked at tables of Kas, you're dealing with these exponential notations, you're spanning orders of magnitude, right? 10 to the negative 10th, 10 to the negative 2. And so just like we've seen this before, that was a problem with hydronium concentrations, so we used pH. So similarly, we can apply the power scale to these and define what's called pKa and pKb. So P means power, and it literally applies that we're doing the negative log of whatever's after the P. So it's called an operator, where you act on something as an input, kind of like this is a function that, say, takes in a variable, Ka in this case, and you take the negative log of it. And so you can take Kas and Kbs, take the negative log of them, and turn them into pKa and pKb values. So let's look at some examples. What is the pKa of acetic acid, CH3COOH, and what is the pKb of acetate, CH3COO-? So I want to know the pKa of my CH3COOH. And so pKa is equal to the negative log of the Ka. So P always just means negative log. Red. So always just means negative log. So we just take the negative log of that value. If we want to know the Ka of something like acetic acid, we can always look up that piece of reference information. CH3COH was 1.76 times 10 to the negative 5th. So I take the negative log of that, and I get that the pKa here is 4.75. Similarly, for pKb, that's the negative log of the Kb. CH3CO-, we did in a previous example of determining the Kb from the Ka here. So you can't look it up necessarily in most tables, but we calculated out that it was 5.68 times 10 to the negative 10, and we get 9.25. And so one of the things that's nice about pKas and pKbs is, when we're comparing Kas, these values are all these scientific notation, exponential notation values, and it can be hard to kind of, which one's bigger, which one's lower, you got to look at the exponents, it can be hard to kind of focus in on it. But pKas and pKbs, it's the whole motivation of like pH. It's just a simpler number that's generally between 0 and 14. It's just easier to kind of look at. And low pKas correspond to stronger acids. Lower pKbs correspond to stronger bases. One of the things you'll note if you look at these values for a conjugate pair, again, only if it's a conjugate pair, pKa plus pKb equals 14. So 9.25 plus 4.75 equals 14. That is not an accident. It's related to the fact that you can, that this Ka times Kb gives you Kw. It's the same relationship, just if you apply the logs, you would work it out like that. So when we're dealing with pKas, smaller pKa values correspond to stronger acids, in much the same way that low pH corresponded to more acidic solutions. And so the real value of pKas and pKbs is that, when we were comparing these acids before, we had to look at, say, the exponents and look at the least negative exponents for strength, which can be a little counterintuitive or kind of trip you up. But if we just take the pKas, 2 is less than 3 is less than 9, so H3PO4 is the strongest of these acids. It's also easier to kind of parse out the relative differences in the strengths. So we can see that while HF is weaker than H3PO4, because that number 3 is greater than 2, the difference there is only one pKa unit, whereas it's a whole 6 pKa units to HCN. So that sort of HCN in this list is a distant third. and it's much easier to compare with pKa. So a lot of times when we're talking about them, especially if you only want to compare acid strength, it's much more frequent and much more common to see pKa's as opposed to Kas. Now, functionally, when you're doing things like working equilibrium problems, actually determining pH, those sorts of things, you do need to use the Ka value because that's actually in the equilibrium constant. But pKa's are going to be something that you would see much more frequently people use just to compare acid strength. That, hey, this has an acid pKa of 5, it's better than this acid that has a pKa of 10, and those sorts of things. And pKb is the same idea. Lower pKb's correspond to stronger bases. And one thing, strong acids have negative pKa's. So they are so strong, it's so low that the pKa is negative.
Another video down, no participation questions here. See if there's any in the next video. See you there.